So this kind of the analysis is quite kind of interesting. So you can see we can as long as we can describe this flow system by using some mathematical way. And we can input perturbation and then try to see what happened to this perturbation once they input into this flow system. And then based on the boundary condition we have, we can check what our sigma I, right? Sigma I, because since we have this for this flow system, we can describe. Based on this flow system, we have this boundary condition have to be satisfied. And this is dynamic boundary condition, right? This is dynamic boundary condition. So dynamic boundary condition give us the solution, give us relationship with sigma with lambda. That's one kind of dispersion relation. So we can evaluate this sigma, right? This sigma by using this equation. And once you evaluate, you can see quantifying has been cancelled out through the equation only of common factor. Just take a note there, reduced to 4. I think you can did a little bit analysis, like kind of a mathematics. You can simplify this. I think just try to using a common factor, this sigma minus u1, right? And then 2 pi over lambda, and then once you have a common factor, extract out, and you will get this, and plus a low 1g here. I think you can do that. Similar here. If you extract the common factor sigma u2, 2 pi over lambda, right? And what else? I here, low 2 here, right? And then once you extract a common factor and the rest combine these two terms together, you end up with this. End up with this. So that's our dispersion relation. After kind of simplify, the equation we just have. So here is a sigma for the second order polynomial, right? We have sigma squared, right? Sigma squared. So we can using the second order solution for the second order polynomial, right? 多项式的二次式，对不对？2a 分之负 b 加减根号 b 平方减 4ac。So sigma is so here is try to evaluate sigma by using the second order polynomial. So we have the second order polynomial here, and then we can get the second order polynomial solution for sigma. Sigma is this part plus and minus this square root. So that's finally we can have this. We can have this. This is our from the dynamic boundary condition. We have a sigma is function of lambda, right? Function of lambda. So that's a kind of a dispersion relation. And these two terms, can also become summation together to give you this term here. You can do that. It's easy. I think that it's more difficult. Just try to do this, minus this, and then eventually get this. And here I switch our low 2. This is low 2 minus low 1. Here we become low 1 minus low 2. So this minus sign become part of this sign here. And this two term will become this minus this become minus of this. I think it's just pure mathematics. I think you can do that. So that's our dispersion relation. Let's simplify. I think we can write down this dispersion relation. This is new, right? And write down this dispersion relation. Now sigma is what? Sigma is equal to low 2u2. Low 2u2. Right? Plus low 1u1. Divided by low 1 plus low 2. And then square root of g Okay. Rho 1 minus rho 2. Intermediate relationship and rho 2. Okay, where rho 2 plus rho 1, rho 1 minus rho 2. And then multiply G lambda over 2 pi. This is the gravitation term here. Okay. I need to go to here. And then rho 1, rho 2. So minus rho 1, rho 2. Okay. And then rho 1 plus rho 2 squared. Squared. And U2 minus Uy squared. U2 minus Uy squared. Okay, I think I can. This is our okay from the all the boundary condition. I introduce small perturbation into this flow system. Current equation is what? Laplace equation. Boundary condition including a far field boundary condition. Okay, as well as what? At the interface we have what? We have the kinetic boundary condition and dynamic boundary condition. And this is from dynamic boundary condition. Okay, so this is the solution. Once you introduce a small perturbation, and this small perturbation, the sigma, okay, will be equal to this. Okay, this is discussed. Let's discuss. Okay, the first case. Okay, based on this dispersion relation, let's discuss. If you have a U1, this is the case 1. Okay. U1 equal to U2 equal to 0. And the rho 2 is equal to 0. That's case 1. What's this case mean? You have the U, right? U1 here, U2 here. You have the interface here. You have the rho 2 here, rho 1 here. Right? There is no velocity. No velocity. However, rho 2 is equal to 0 compared with rho 1. That means what? This density is very small, right? So we have, for example, we have air, but we have water here. And water and air, the density is, the difference is so big, this density can be neglected. Can we do that? Okay, so we have no flow field, that means that's stationary. Right? Stationary fluid. Stationary fluid, that means no moving. Flow didn't move at all. Right? Flow didn't move at all. And then only the water below. So at the beginning, this water is an interface like this. I introduce a small perturbation. Right? And to see under this kind of flow system is what happened. Okay? So based on this, as you can see here, our rho 2 equal to 0, right? Rho 2 equal to 0. So this is rho 2 equal to 0. This term is dropped, right? Rho 2 equal to 0. So this term here gives you U1 only. Right? U1 sigma is equal to U1 plus rho 2 equal to 0. Rho 2 equal to 0. What happened? Rho 1 divided by rho 1 give you what? 1. G lambda. Rho 2 equal to 0. Disappear, right? So we have this. So sigma is this. The sigma is sigma is what? It's a sigma r plus I sigma I. I is the imaginary. It's a complex number. And here we have this real number. And here is a real number. So here we don't have this, our sigma I is I. Okay? That means it's not greater than 0. Okay? Under this case, as you can see here, sorry, I made a mistake. U1 should be equal to 0, right? Right? U1 should be equal to 0. Right? Made a mistake. Okay? For this case. So it's all what? It's all real number. Okay, so our sigma equal to positive negative square root of G lambda over 2 pi. Okay? So as you can see here, okay, it's just like a traveling wave, okay? Since this is our sigma is only the sigma r, right? So this is sigma r because we don't have an engineering part. It's a real number. It's a real number. So when I perturb this flow, and then when I perturb, what happened? This small perturbation wave will be propagated along by using these two wave speed. What's the wave speed? Positive mean it will travel to the right. Negative mean it travel to the left. Okay, so they have the traveling wave, okay, to the right and to the left, and so that's a case for this. And this is stable, okay, this flow is stable because our sigma I is greater than 0. Okay, sigma, you just propagate, okay, for this case. Okay, its potential closed. So that's a stable, this interface is stable. Okay, this is case 1. Let's try the case 2. What's the case 2? Case 2 here. Case 2 here, we have the low 2 equal to 0 again. However, okay, I have a low 1 and low 1 is not equal to, U1 and U2 is not equal to 0. Okay, that means, okay, I don't have any constraint for U1 and U2. Okay, I only constraint, I don't have U1 and U2 can be flowing. Okay, I have a velocity above, it's moving. However, I only have the low 2 is equal to 0. That means I have air again and water. And the air, this is a kind of special case, okay, has some fluid above. The density is compared with the density below is much, much smaller. Okay, like air is water. And this air is flowing and water is moving with some speed. Whatever. Okay, this is case 2. Okay, this is case 2. Again, when the case 2, here, okay, I messed up. I need the alcohol to finish this. Okay, low 2 is equal to 0, right? So sigma here only low 2 is equal to 0, and this low 2 is equal to 0. So this becomes low 1 u divided by low 1 sigma is equal to u1 only, right? And plus minus here, low 2 is equal to 0. Low 2 is equal to 0, so become low 1 divided by low 1 is equal to 1. So again, the G lambda over 2 pi here. Okay? Low 2 is equal to 0, so we don't have this term, so we have square root. Okay, so that's our sigma. Okay, for the case 2. Okay, so our sigma for the case 2 is what? It's this. Sigma is u1 plus and minus square root of G lambda over 2 pi. Okay, again, you can check sigma is equal to, okay, sigma r plus sigma I, right? I sigma I. So here, this is real number. This is another real number. If you plus and minus a real number, this is all real number. Okay, so sigma again is equal to 0. Okay, so this interface, once I introduce this small perturbation, this interface stays stable. Only the difference from the previous case, for this node without any speed, okay, my wave speed is equal to this. Okay, however, if once I have the speed u1 and u2 below, and my wave speed become like this. Okay, wave speed. So as you can see, either u2 is blowing very hard. Okay, 当你这个上面的风一直吹得很强 it didn't influence your interface at all, the wave speed at all, because in this equation we didn't see any u2, right? Velocity. So if you have a very wind blowing, okay, didn't affect this wave speed at all. kind of contracted what we see, right? Sometimes we expect when the wind is blowing very fast, it will generate wave or something. Okay. But this is only for the small perturbation. Okay. When you have a large perturbation, of course, the wind will be impinging on the wave, right? That will have another interaction. But we only have very small wave. Okay. So wind didn't influence this small wave. Anyway, so this is for the case 2. Okay, we have this kind of conclusion. Our sigma still stable, right? Sigma still stable. Okay, case 3. What's the case 3? What's the case 3? Case 3 is what? Case 3 is the low 1 equal to low 2. Low 1 equal to low 2. Okay, so not equal to 0. Okay, and U1 and U2 is just arbitrary. Okay, what the physical meaning for this? What's physical meaning for this? Low 1 and low 2 is equal. That means both of this flow is the same medium. Either this is air, this is air, right? This is air. Okay. If this is water above, this is also water below. Okay, the same medium. Okay, only difference what? Velocity. Higher velocity. Okay, U1, U2 is arbitrary choose. You can have the faster below or the smaller velocity above, or vice versa. You have high speed above, small speed below. Okay, then so whatever. U1, U2 is arbitrary, but however we have low 1 equal to low 2. So what we have here, low 1 equal to low 2, it means this is equal to low, right? This is low, and this is low, this is too low, so it becomes 1/2 part. Okay, you can substitute use low 1 equal to low 2 equal to low 10, and then you can simplify this solution to become 1/2 U2 plus U1, right? Low 1 equal to low 2. So we don't have this gravitation term only. Okay? So something interesting happened here, right? We have a mass sign here. Low 1 minus low 2. And low 1 equal to low 2, so it becomes low squared, right? Low squared. And low 1 plus low 2 is become too low squared. What 1/4, right? This is 1/4. Low square is cancelled, we have 1/4. So I have 1/4 here, right? Is that right? Yeah. Low 错，哪里写错 ？Anyway. Right? I have this kind of. Okay? I have this. And then this is all parity variable, right? Because the momentum U1 and U2 is which is bigger. Okay, this is all parity variable. And this becomes what? I here. U1 plus U2. I here. And this becomes 1. Should we have the should be part absolute variable for this. Let me kind of put the absolute variable for this. Is that right? Should be supposed, right? Because once you want to take out this square root, you should be positive here. Okay? So as you can see here, what happened? Sigma right now is has a sigma r here. Sigma r here. Right? Okay. So sigma I and the chance is a parity variable, right? Chance to parity variable. So here we have the sigma is equal to this, okay? The sigma is equal to this. And then for this number here, no matter, because we have a part, we didn't put the square absolute value here, because once you put a square absolute value here, the only difference, if you don't put it, if this is negative, become the minus sign here, change it to sign only, so it doesn't matter, okay? So we have this sigma, okay, for this case 3. So case 3 is what? Case 3 is we have the same median, but only have the velocity shear, okay? One side is speed higher, speed is higher, one side is lower, we have velocity different. U1 and U2, so U1 and U2, okay? No matter U1 and U2 which is bigger, right? It's always a possibility what? This sigma is greater than 0. Okay? That means what? When sigma is greater than 0, we have, according to our normal mode analysis here, at the beginning, right? Here. Sigma I is greater than 0, the wave will be growing exponentially, right? Sigma I is greater than 0, this is time. So our amplitude, initially at the time equal to 0, our amplitude is epsilon. And then when the time as time going, right? Since sigma I is greater than 0, our amplitude become epsilon times this exponential function. So that means our amplitude will be growing with time. Okay? So that's unstable. Okay, so this case is unstable. So always when we see the velocity shear, okay, and then this is unstable. Velocity shear. So the one case is what? One case we have this velocity shear. Okay, we have high velocity above and low velocity below. Okay, this is called mixing layer. Okay, in the fluid mechanics, we call this is mixing layer. Okay. This is a very kind of example for this kind of shear layer flow. And so this kind of shear layer flow didn't encounter any boundary because it's free shear layer. So when you're talking about free shear layer flow, that means we didn't interact with the boundary, only to have the flow is velocity different within the flow field. Okay, so this has become one of the what? The flow field can happen when once you have the velocity difference, and that can be applied to many. Okay, once you have velocity difference, you can generate a wave here, and this wave will be eventually grow. And I can show you the picture. Okay, the simulation of the experiment. Okay, later. Okay, I can show you the picture. Okay, I can show you one picture first. This is the mixing layer. This is mixing layer. I have a high speed above, low speed below, and then okay, I want this. So this is, once they start have a small perturbation here, this is small, and then this small perturbation eventually grow up, right? You can see this is grow up. And then the vortex is growing and growing. Okay? So that's a mixing layer problem. Okay? So mixing layer, okay? So we have this kind of flow, okay? And this mixing layer with a small perturbation here. And then eventually this will be generated. Okay. And this is potentially closed. Okay, the vortex will become bigger and bigger and bigger. So that causes a lot of entrainment. Fluid A and fluid B, okay, we call this the entrainment. Entrainment of fluid between these two fluids. Okay, and then when fluid B entrained into this string here, and fluid B entrained inside here, has a very good mixing. So combustion is like, okay, you have fuel, you have oxygen, and fuel and oxygen have to mix. Okay, you need a shear layer to generate all this kind of mixing mechanism to stretch all these flow fields and then increase our interface area. And then this interface area is growing with time. Okay, based on the analysis. Okay, so that will be the one, okay, called the mixing layer interface. Okay, and then in the year of the 1970 or 1980s, from the 1980 or 70 to 1990 something, okay, this topic is very popular. As you can see, you are Professor Miao student, right? His PhD thesis is this. Okay, 他的博士论文就做这个。Okay, and Professor Xiao previous, okay, is doing is a jet. Jet is what? You have a flow like this, jet flow. And jet flow is what? It's also one kind of mixing layer, right? We have a velocity here, smaller velocity here, high velocity. So you have a mixing here. You have a two mixing layer, right? And they will interact with each other because for this interface would be generate like this. Okay, and this interface will generate like this, and this maybe have some interaction. Okay, that's causal. Here is a popular problem. Okay, in the fluid mechanics study. Okay, and here this kind of mechanism or this study all come to so-called flow control study. We call this flow control. Okay, what's the flow control? Flow control is we try to input a small perturbation into this flow system to control the flow field. That's called the flow control. We don't need a large amplitude. We need a small perturbation. Okay, and then this small, by using small control, we can introduce a small perturbation into the flow field. Okay, for example, Professor Xiao, he passed away already. His PhD thesis, okay, he's doing what? He uses acoustic here. There's an acoustic. Acoustic means using a speaker, right? He generates spiritual wave here and try to control all this instability. Okay, and my PhD thesis advisor, his famous okay, paper is what? He's doing the mixing layer. This is what he did before. In the 1984, it's published a paper in JFM, Journal of Fluid Mechanics, and it's very popular at that time. So what he did is what? He tried to perturb the flow mixing layer. As I show you, it will be U1 and U2, right? And you will generate this, we call the structure. Okay? Very beautiful, organized structure. Sometimes we call this structure is a coherent structure. Okay, very coherent structure. And then it kind of perturbed by using any kind of flow. For example, perturb in the flow field. Or you can also the perturb in the boundary. Okay, try to generate any kind of perturbation. And this perturbation, we notice there's a frequency here, right? Frequency. And this frequency, when you have a probe, if you're using the hot wire here, and then when the flow is passing by, it will generate this kind of flow signal. And this signal is a time signal, right? And we have time. So this is a T, and 1 over T gives you the frequency. Okay, we call this for this flow field, we have this kind of fundamental frequency. Okay, and at the beginning, they can introduce a fundamental frequency here. I introduce a small perturbation, and this perturbation fundamental frequency is the same as this. What happens? They will fix the formation for this star. Okay, and then once you put the so-called subharmonic, there's in 1984 he used the subharmonic. Subharmonic might be instead of F, this fundamental frequency, they're using the subharmonic 1/2 of the force, even or 9. Okay, any integer number divide F, and what happened? What happened?